Okay, good morning, ladies and gentlemen. My name is Gianluca Cusatis, and I'm chairing the EMI 2013 conference. As you know, the theme of this year's conference is mechanics for sustainable and resilient infrastructures. And throughout the next 3 days, we will try to answer the following question. How can we, as mechanicians, contribute to make the nation's infrastructures safer, more durable, more affordable, and more environmentally friendly during the entire life? In trying to answer this question, and thanks to the contribution of all of you, we have organized an amazing technical program featuring 2 poster sessions, 10 parallel tracks, 6 plenary lectures, and several keynote lectures in the tracks. Needless to say that we would not have achieved these results without the support and help of the ASCE Engineering Mechanical Institute and Northwestern University. For this reason, I would like first to ask the EMI President, Professor Roger Ghanem, to say a few words on behalf of the EMI. Professor Ghanem.
Good morning and welcome to the conference. First of all, on behalf of the Board of Governors, whom I'm representing here, I would like to thank Gianluca and his team for organizing what promises to be an amazing conference. The technical and social programs and the weathers are all collaborating. Second, and also on behalf of the board, I'd like to welcome you all to the Engineering Mechanics Conference of this year. The board is elected by the members and does the business of the Institute on behalf of the members. And the next election, the due date for your votes is August 12th, is set to place 2 new board members on the board. And I urge you all to take this matter very seriously and cast your vote. You will be receiving an email from EMI in the next week or so giving you renewed instructions as to how to proceed with this. So this is the first line of engagement that allows your vote to affect the way the business of this institute is carried out. So I urge you to remain engaged and proceed with your vote for the election. Second, at our meeting yesterday, the board has decided on new steps to strengthen the engagement of the members with the growth and sustainability of the Institute. And a number of those items are worth mentioning because they will only be successful if indeed sufficient members are engaged and support their and support them. So the first one is the webinars and workshops that are facilitated and made possible through ASCE. In our opinion, these are a very important line of engagement that allow the members to express themselves, to capitalize on the machinery that ASCE has that would allow us to connect with a much wider network of colleagues and professionals who could utilize and capitalize on the body of knowledge in this community. So you will be receiving a number of emails in the next 2 or 3 weeks from the Institute that lay out a number of steps that we hope would facilitate and would make your engagement in that capacity painless. So I urge you to consider those opportunities very seriously. And if you need any, if you have any thoughts or any feedback on how the board or the institute could better serve you, better express your desires, your technical expertise, please do not hesitate to get back to us and provide your feedback. On that note, I welcome you again to the conference. I wish you all a very pleasant and interesting meeting. And I give the podium back to Gianluca.
Thank you very much, Professor Ghanem. Now it is my pleasure to ask the Dean of the Northwestern McCormick School of Engineering, Professor Julio Tino, to deliver the welcome remarks on behalf of Northwestern University.
Yeah, as Gianluca said, my name is Julio Tino. I'm the Dean of the McCormick School of Engineering and Applied Science. And it is my distinct privilege to welcome you to Evanston, to Northwestern University for the 2013 Engineering Mechanics Institute Conference. I think Northwestern is uniquely suited to host a conference that requires a high level of collaboration. And this year's theme, Mechanics for Sustainable and Resilient Infrastructures, brings together mechanical, civil, environmental, material science, among other areas. And at Northwestern, and I hope you have a chance to walk, you're in the south part of campus, which is mostly humanities, theater. The north part is more science and engineering. We are unique among the schools in the sense that all engineering, chemistry, and physics are connected in one building. That did not used to be such a competitive advantage as is now, because proximity creates all sorts of interesting connections. And this is what conferences are all about. I mean, we can keep up by reading journals, but at the end of the day, the number of useful connections that you make in a conference are hard to beat. That brings the concept, sometimes I have used, that everybody here is at the frontier of something. And that frontier of something, if you consider the envelope of all of those, is, to paraphrase Stuart Kauffman, he was a theoretical biologist, so is the accessible possible. So the accessible possible for Kauffman was, you start with the primordial soup, methane, water, whatever, and then you go to more substantial, more elaborate molecules, but it's very hard to jump from that to an octopus, okay? You go step by step, making connections in that accessible possible. And the connections that you're making here allow you to go one step further in whatever discipline you are. People have sort of documented this. I do not know how many of you heard of Stigler's law. Stigler's law, Stigler was a fellow further south here in Chicago. Stigler's law is that no scientific discovery is named after the original discoverer, including Stigler's law that was put by a fellow named Robert Merton in Columbia. Merton is a remarkable guy. Things like unintended consequences, role model, self-fulfilling prophecy, terms that you think have existed forever, he coined. So the idea that when you are all together, you will have ideas and almost at the same time come up with the same ideas as other group. That's something that has been well studied in science. Some of you may have heard, for example, about studies that have been done about Kelvin, Lord Kelvin. He communicated lots of things, but he was part of a circle, like all of you here, actually closer together in those days, and out of all the things that he communicated, there were like maybe 50 that were communicated at the same time by another one. But that doesn't diminish Kelvin's greatness. What proves is that in order to even prove or reprove 50 of the 300 things that he did, you needed a subset of people who are almost as good as he was. So that's the value of conferences like this. I mean, we can all get together via Skype or whatever, but nothing beats the proximity of a conference. And that's why I am pleased that we had the opportunity to host this in here. And while the conferences are valuable, they also take an enormous amount of work. And I want to take a moment to thank the organizers, in particular, Northwestern's own Gianluca Cusatis, who serves as the chair of the conference. Thank you, Gianluca. So, again, it's my pleasure to welcome here to the Northwestern campus, and I hope that you will have an engaging and productive couple of days in Evanston, and that the connections that you make here serve you, all of you, in your research going forward. Welcome to Evanston. Thank you.
Thank you very much, Professor Ottino. This concludes the opening session, and I can declare the EMI 2013 conference officially open. This leads us to the first plenary session that will be chaired and moderated by Professor Paolo Gardoni from the University of Illinois at Urbana-Champaign. Paolo. I think it works.
Thank you, Gianluca, and good morning, everyone. As Gianluca said, I would just like to start by introducing myself. I'm Paolo Gardoni from the Department of Civil and Environmental Engineering at the University of Illinois at Urbana-Champaign, and I'm serving as the moderator of this opening plenary lecture. I would like now to introduce our keynote speaker and the two panelists. We have the distinct pleasure of having Professor Armen Der Kiureghian as the keynote speaker for this plenary lecture. Professor Der Kiureghian is the holder of the Taisei Chair in Civil Engineering at the University of California, Berkeley. He received his PhD and MS in Civil Engineering from the University of Tehran, Iran, and his PhD in Structural Engineering from the University of Illinois at Urbana-Champaign. Professor Der Kiureghian's research is in a broad range of areas, including structural and system reliability, risk analysis, random vibration, and earthquake engineering. He is an elected member of the National Academy of Engineering since 2011. The title of his presentation is Tail Equivalent Linearization in Nonlinear Stochastic Dynamics. The lecture provides a review of the tail equivalent linearization method and discusses its advantages, limitations, and potential for future development with relevance to application involving earthquake and wave loading. The two panelists in the plenary lecture are Professor Ross Korotis and Professor Bazan. Professor Korotis is the Denver Business Challenge Professor in the Department of Civil, Environmental, and Architectural Engineering at the University of Colorado Boulder. He received both his undergraduate and graduate education at MIT, and he's an elected member of the National Academy of Engineering since 2002, in light of his contribution to probabilistic modeling. Professor Bazan is the second panelist. He is the McCormick Institute Professor and the Walter P. Murphy Professor in Civil and Environmental Engineering, Mechanical Engineering, and Material Science and Engineering. His research interest is in the mechanics of solid and structures, and he's an elected member of the National Academy of Engineering since 1996 and of Science since 2002. Please join me in welcoming Professor Der Kiureghian.
Good morning. I'm very glad to be here, and I'm very grateful to the organizers and the EMI board for inviting me to give this talk. I would like to first acknowledge my students, Kazuya Fujimura and Luca Gare, are past PhD students who have worked on this topic, and Marco Roccardo, who is here, is a current PhD student, and he's trying to put a more rigorous foundation for the method and to extend it to some new applications. The work has been primarily supported by the earthquake engineering Pacific Earthquake Engineering Research Center at Berkeley. Stochasticity and nonlinearity are characteristics of many engineering problems, structural and mechanical engineering problems. In some sense, one can say they are mother of all problems. Example applications include inelastic structural response to strong earthquake ground motion, response of offshore structures to wind loading, where you may have not only material but also geometric nonlinearities because of the moving wave surface, wave height, and response to turbulent wind, and I'm sure many other problems. My particular area of interest has been earthquake engineering. So the examples I will give will be more relevant to that area. Of course, there are a number of methods that have been developed for nonlinear stochastic dynamic analysis. I will make a very, very brief and probably unfair review shortly, or brief outline of what these are. But most of these methods either are restricted to special cases of nonlinearity or system, or are limited in application to cases, for example, that are not applicable to reliability applications, extreme events. So that's why I think there is need for a new method, and this has been motivation behind this work over the past few years. I will start with, as I said, a very, very brief outline of existing nonlinear stochastic dynamic methods, most probably very incomplete. I will focus a little more on the equivalent linearization method, because what I'm proposing is sort of an equivalent linearization method. I will then lay the stage for the method by outlining how we characterize linear systems, because this is how we will define the equivalent linear system. I will describe very briefly the first order reliability method, because tail equivalent linearization method is based on that approach. This will require that random processes be described in terms of random variables, and that requires a process of discretization of random processes. I will briefly talk about that. And then in one slide, having done all this, laid out the foundation, in one slide I will show you what we mean by tail equivalent linearization. And then I will spend most of my time talking about the various characteristics of this tail equivalent linearization method and tail equivalent linear system. So these two acronyms I will be using as shorthand notation for these concepts. I will have also a brief outline of what are the main challenges, the difficulties in using this method, and what are its limitations, and then I will conclude. There are a number of methods that have been developed for nonlinear stochastic dynamic methods. Several of these classical methods are listed here: the Fokker-Planck equation, stochastic averaging, moment or cumulant closure, perturbation. These are well developed. However, the first three methods are typically restricted to rather small systems. They become really, really computationally intense if you use large number of degrees of freedom, maybe 1 or 2 degrees of freedom in most cases. And they're also restricted to the kinds of nonlinearities that you can use. Not every kind of nonlinearity can be handled. Perturbation is somewhat broader, but you really cannot account for large uncertainties in perturbation. A method that has gotten wider application, particularly since 1980s, mid-70s and 80s, is the equivalent linearization method. In the next slide, I will provide a bit more detail about this method. And of course, there is Monte Carlo simulation method always as a backup. It requires extensive computations, particularly if you're dealing with high threshold, small probability problems. But here again, there are a number of works in recent years, sort of smart Monte Carlo methods that are available. In the work I will present, in some cases, I will show you Monte Carlo simulation results as representing sort of the exact results to compare the approximations that we will make. This, of course, is incomplete. There are other methods of nonlinear stochastic dynamics. For example, there's quadratization. Paul Spanos has worked on that. There are other methods that exist, and so this is not a complete list. The equivalent linearization method is rather well established in mechanics. Kogge and others have had pioneering works in this area. Essentially, this is an approximate method where you approximate the response of the nonlinear system in terms of some equivalent linear system. That equivalent needs to be defined, what we mean by equivalent. In general, the equivalent linear system is defined by somehow minimizing some difference between the linear and nonlinear responses. And different methods are characterized by what it is that you try to minimize. The conventional, the most widely used equivalentization method minimizes the variance of the error between the linear and nonlinear responses. So you take the difference between the two responses and you look at the variance and you minimize that variance. In implementation, this requires making an assumption about the distribution of the response, and typically that has to be the Gaussian because it simplifies all the calculations of the minimization. The two references have been listed here. These are our key references that have made this method quite popular. Particularly Weike Wen has popularized this method. This equivalentization method works well for the variance of the nonlinear. If you're estimating the variance of the nonlinear response, it provides quite accurate results. However, if you're interested in tail probabilities, if you're interested in knowing what is the probability that the response will exceed a high threshold, then this method does not work well. And does not work well particularly because of the Gaussian distribution assumption. We all know that even if the input is Gaussian, the output of a nonlinear system is not Gaussian. And so this Gaussian assumption is rather limiting. And people have, of course, recognized this, and a number of papers are available that try to extend this. I have listed two of them. Arvid Ness has suggested that rather than looking at the variance, probably we should look at higher moments of the response. And he's done this he's been able to do it for a particular kind of nonlinear system, an elastic nonlinear system where the nonlinearity is the restoring force has a parabolic quadratic form. A polynomial form, I'm sorry. Because he's looking at higher moments, so that the emphasis is placed in the tail, and so he's able to get better results in the tail. But the method is rather restricted again because of the polynomial form. Another idea has been put forward by Kashati and his co-authors, where they proposed minimizing the difference between outcrossing rates at a presumably high threshold. And so again, by minimizing at a high threshold, you're able to get good results in the tail. However, it's not clear how you compute the outcrossing rate of the nonlinear response. In fact, their paper, the title of their paper is a new philosophy. It's more put forward as a philosophy rather than a practical computational method. The method that I'm proposing here, the Taylor linearization method, this method defines the linear system by equating its tail probability to the first order approximation of the tail probability of the nonlinear system. So this is the basis of this method. And because it's dealing with the tails, therefore the accuracy is enhanced in the tail region. Okay, so let me now lay out the foundations on which I will be developing this method. First, we want to define a linear system. Think of a very general linear system and somehow supported, and it is subjected to, for the time being, just one excitation f of t and one response x of t. Given this particular input-output pair, so we have to focus on one input and one output, then a stable linear system can be characterized in two different ways. One is in terms of an impulse response function, which is the response when the excitation is just a delta function, an impulse. And the other is, in frequency domain, is the frequency response function, FRF, that is the amplitude of the steady state response when the excitation is a complex harmonic function, e to the power I omega t. So if you have either of these functions for a stable linear system, then you have completely characterized the system. You don't need to know the geometry, boundary conditions. So for any input, you can compute the corresponding output. This, I think, is very well known, but I'll be using this concept in this paper. The second element that we will be using is the first-order reliability method. This is, again, well-developed method for structural reliability analysis. Time invariant. So this is an approximate method for solving time invariant reliability problems. There's no time involved here. So think of x being a vector of random variables. We define a limit state function such that when that function takes on a negative value, then the failure happens. So the failure is defined in terms of a limit state function taking on negative or zero values. Then the probability of failure is equal to that event, that limit state function take on a negative value. This picture describes the concept in terms of geometry in the space of these random variables x1, x2. These contours are representing contours of the probability density function of these random variables. The red line, the limit state surface, is where this limit state function takes on zero values, and the gray domain is the failure domain. So the task here is to compute the probability of the outcome of the random variables being in this failure region. The first order reliability method solves this problem by making first a transformation. We make a transformation from the X space into the space U of a vector of standard normal random variables. There's no approximation involved here as long as and it can be done as long as the random variables are continuous and have a strictly increasing CDF or joint CDF. So you make a transformation from this space on the left. I think this battery is dying. I have a similar one, but I don't think it will. Well, yes. So we go from X space to U space, and the advantage of doing this is that in the U space, the probability densities have contours that are spherical, hyperspherical in high dimensions, if you can imagine. And so it's a canonical space, and in this space there are some simple properties in terms of probability computation. Of course, we also transform the limit state surface into the standard normal space, and I use capital G to denote that. Next, we find the point nearest to the origin in this space. We call this the design point, and you can see that's the point there. And we linearize the surface at that point. The so-called reliability index, beta, I will be using this notation later, is the distance from the origin to this. And you can imagine in the standard normal space, the mean is at 0. So the farther you are from the mean, the farther the failure domain is from the mean point, the more reliable it is. So this distance is a measure of reliability. The higher beta is, the higher the reliability. And the first order approximation of the failure probability is described by the probability of failure defined by that hyperplane, which would be sort of a half space, probability of half space in the standard normal space. And that depends only on the distance from the origin because of the rotational symmetry and so on. So it turns out that the first order approximation of failure probability is just the standard normal cumulative probability function evaluated at minus the distance from the origin. This works well because of the fact that in the standard normal space, probability density decays exponentially with distance from the origin. So as you go far away from the origin, these discrepancies between the actual surface and the hyperplane become negligible. So, to use a time-invariant reliability method to solve stochastic dynamic problems, somehow we have to discretize so that the stochastic process can be represented in terms of just random variables. So here is how we do this. I will be doing it for a zero-mean Gaussian process. In general, a zero-mean Gaussian process can be described in terms of this this decomposition in terms of product of a deterministic basis functions that carry the time evolution of the process and the time invariant vector u of standard normal random variables that brings in the stochasticity. So this is a way of separating time variation in time, evolution in time, and stochasticity. There are different ways of doing this. For example, in time domain, one way is to define these basis functions SI as responses of a linear filter, modulated responses. So this h of t is the impulse response function of a filter, and q is some kind of a modulating function that modulates the process in time. And the picture down there describes what this means. We have discretized time. At each time point, there is a random pulse, and the filter responds to that pulse. And you can imagine you sum up, because that first equation is nothing but that summation. So when you sum up, you end up getting something that looks like this. This is actually a process simulated exactly as you saw. And I should mention, pay attention, this process is not only stationary in time, but also, non-stationary in time, but also non-stationary frequency domain. The frequency content initially is higher frequency, and later we have a longer period content. This is achieved by changing the parameters of the filter with time. Another way of doing this discretization is in the frequency domain. This is a very well-known way of decomposing the process into its frequency components, sine, cosine functions with random coefficients in front. And so this is one way of, particularly appropriate for stationary processes, one way of representing a power spectral density in a discrete way. So this is how either of these methods is how we use to represent the random process now in terms of deterministic functions and a vector of standard normal random variables. The next thing is, well, now how do I use the first order reliability method to solve stochastic dynamic problems? Well, first, remember that we discretize the process in this way. Second, obviously the response now is a function of time, but also implicitly a function of these random variables u. And there could be many of them. There could be several hundred or thousand of, depending on how you discretize duration and so on. So you could have many such random variables. In the applications I will show, we typically have somewhere between 100, if you do it in frequency domain, it could be 500 or more. We do it in the time domain. So this is the response to the discretized excitation. And this is what I call the tail probability. So the tail probability, the way we define, is the probability that at a given time t, the response exceeds a threshold x. We're interested in that probability. It turns out that this is the kernel for doing all kinds of other statistical analysis of stochastic response. So this is the important quantity to compute. Well, we compute this, we formulate this in a reliability context. Here is the limit state function. Because the random variables are already in the standard normal space, then I use capital G. So it's simply x minus capital X. You can imagine that if the response exceeds the threshold x, then failure has happened. So that is the tail probability formulation. This now, the tail probability becomes simply the probability that the limit state function takes on a negative value. And we find the design point, and we find the reliability index. I've shown all of that, similar to what we saw. The exception that here the limit state function has the threshold as a parameter also. Of course, threshold is a deterministic quantity we've selected. So limit state function has the threshold as a parameter. Strictly speaking, I should also make it a function of t because it depends where we select time t, but t is less important than the threshold. I'll explain why later. So I don't include t at this time. So we do this, and then the failure probability is the standard normal cumulative probability evaluated at minus beta, and beta is a function of x. So right here you can see that the distribution is not Gaussian because beta is not necessarily proportional to x. Now, an interesting thing happens if we look at a linear system. Let's begin with a linear system. So what happens in a linear system? You can use superpositions. So the response of a linear system, is simply A times A times U, where A is sort of the collection of responses for these specific deterministic functions, as if these were the excitation. You compute the response, and that becomes A. So that is a particular form now. The response is a linear function of U. And the limit state function is a linear function of U. Therefore, the picture takes this form. That is, for a linear system, the limit state surface is a hyperplane in this very high dimensional U space. And A is the gradient vector of that hyperplane. We find the design point. In this case, there's a closed form expression for it. And we find the reliability index. There's a closed form expression for it. And notice the reliability index is proportional to the threshold. And then we find the tail probability, the phi of minus beta. Beta here is a function of x, is proportional to x. So this means that the response is Gaussian. Of course, we know the response of a linear system to Gaussian excitation is Gaussian, so this shows that. And of course, the result is exact here. There's no approximation involved. Now, it turns out that if you're given the design point, you can backtrack and identify the linear system. That is, if I'm given U star, I can find this vector A, the gradient vector A. And once I have vector A, I can identify the system either in time domain or in frequency domain. Say in time domain, recall that these AIs, elements of this vector AI, are responses to these deterministic functions, basis functions SI. So think of the Duhamel's integral, and this is a discretized version of Duhamel's integral. If I have the right-hand side, that is vector AI, and of course I know these functions SI, then I can determine the unknown values H at different time steps. So I can obtain the unit impulse response function of the linear system if you give me the design point. So I don't know the linear system, but all you give me is the design point. I can tell you what linear system you used. The same is true in the frequency domain. In the frequency domain, it turns out that given AI, you can compute the modulus and the phase angle of the unit impulse, the FRF, the frequency response function. This work, actually, I must credit Luca Gare, my second PhD student. Actually, he was not my PhD, he was my visiting PhD student. He got his PhD from University of Genoa. So in either case, we can characterize the linear system given the design point. Okay, now I'm ready to, in one slide, to tell you what this tail equivalent linearization method is. First, for the selected threshold x and time t, we formulate the tail probability problem as a reliability problem, just as I mentioned before. And that is the picture you have already seen. We find a design point. We find the gradient vector of the tangent plane. Once you find a design point, that is the gradient vector of that tangent plane. And then we identify the linear system that corresponds to that gradient vector A. So either in terms of the unit impulse function or in terms of the frequency response function. So in a sense, the tail equivalent linear system that I will be using the acronym TLS is defined by that hyperplane, by that tangent hyperplane at that point. You can see that the computation is rather straightforward. The most difficult part is finding the design point. And that is what I would like to describe in this slide. How do we find a design point? Well, the design point is the solution to a constraint optimization problem. We want to minimize distance from the origin to the surface, the limit state surface. It's a constraint optimization problem. There are a number of algorithms available for it. And most of these algorithms are iterative, and they make use of repeated computations of the response and the gradient of the response for selected values of U. So here is the challenge, that in order to find the design point, you need to repeatedly solve the nonlinear problem, not many times. Typically, we converge in 10, 15, 20 steps. So that many times you have to compute the nonlinear response. But you also need to compute the gradients of the nonlinear response with respect to these random variables u at selected realizations of these random variables u. And that, if you want to use a method like finite difference, it can be very costly because number of random variables u is large. So what we do is we make use of direct differentiation method. This is, as you know, derivative is a linear concept, so linearization. So it turns out that in order to carry out, to compute the gradient, what you need to do as you do the nonlinear solution at each solution point, you solve a series of linear problems. And we've developed this, and other people have also developed methods for this. And modern finite element codes, I really sincerely believe that modern finite element codes must include gradient computation as a part of them. And OpenSeas is one that we've used, and we have implemented these gradient computations in OpenSeas, and there are other codes that do this. And so gradient computation is a really critical issue for not only this application, but also applications in optimization, in uncertainty analysis, and so on. So here, if you have one threshold, well, maybe you can do, but if you want to get the entire distribution, you have to do this for many thresholds, and that could be very challenging. So we've developed an algorithm for doing this kind of analysis for a sequence of thresholds. Think of an ordered sequence of thresholds. So these are the surfaces corresponding to those thresholds. And you can imagine there's a trajectory of design points. For a linear system, the trajectory would be a straight line. For a nonlinear system, it's a curved line in space, in high-dimensional space. What we do is you first find two of those, maybe at low thresholds, because there it's fairly linear, and you very quickly solve that. And then you extrapolate from those 2 points, and you start your minimization, your optimization solution from that starting point. So it turns out that in 1 or 2 steps, you're able to converge if you make small steps. So this way we can get the solution rather fairly quickly for a sequence of these design points. You need this to come up with the entire distribution. Okay, so now I want to focus on various aspects of this method, the various characteristics, properties of this method that I think they are interesting. First is that for a given threshold, x, and time t, the tail probability of the tail equilinear system is equal to the first-order approximation of the tail probability of the linear system. This is how we define the method. So therefore, this is the reason for the name tail equivalent linearization method. So I want to re-emphasize that. The second is that TELM is a non-parametric method. The conventional equivalentization method is a parametric method. That is, you have to define a parametrized linear system, and then through optimization, you find the parameters of that linear system. TELM, as opposed to that, TELM is a non-parametric method. That is, you don't need to define a parameterized linear system. You actually identify the linear system in terms of its unit impulse or frequency response function numerically. And you will see examples shortly. Next thing is that once you find the design point U star, if you put that back in the expression for the discretized excitation, you find the design point excitation. And this excitation, the meaning of this is that it is the most likely realization of the excitation process to give rise to the event of interest. I will be showing you some examples. This is a single degree of freedom hysteretic oscillator defined by the well-known Book-Wen hysteretic model with these parameters. You will note second line from bottom, here the excitation is white noise, and I'm defining sigma sub 0 as the response, the RMS root mean square response for the linear case. The linear case for this structure, for this oscillator, happens when alpha is equal to 1. But for nonlinear case, we're using alpha equal to 0.1, so this is a fairly strongly nonlinear system. This is the design point excitation for a rather low threshold of 0.5 sigma sub 0. So sigma sub 0, remember, is the RMS response of the linear system, so half that, probably the system is behaving linearly here. And so not much exciting. It's a very small excitation that is needed to put you in that position. If I increase the threshold level to 1.5 sigma sub 0, this blue curve is the design point excitation. Remember, this is the most likely realization of the excitation process to give rise to the event of this tail event of interest. If I go to a higher level, 5 times that sigma sub 0, this is the most likely realization. Now, an interesting behavior you see, they are not proportional for one thing. If the system was linear, they would tend to be proportional curves, but they are not proportional. You will recall that for a Gaussian process, zero mean Gaussian process, the most likely value is 0. So initially, the excitation far away from the point of interest is the most likely value of the excitation is 0 because, well, it's far away, it doesn't have much influence here, and so the most likely value is 0. As you approach the point of interest, which in this case is 15 seconds, t equal to 15 seconds, the excitation becomes bigger and bigger. In fact, you can see that the system, for the nonlinear system, is the last big push that puts the response in the threshold of interest. One other thing, notice that the design point excitation has 0 value at exactly t equal to 15. This is because, well, the excitation value at the point of interest will not have any influence on the response at that point. It takes time in dynamics for the excitation to give rise to influence the response. So the most likely value there is 0. So the excitation goes back to 0 at that point. Then, if you put U star in the expression for the response, that is, you compute the design point response, the response of the system to design point excitation, you get the design point response. And this is the most likely realization of the response leading to the response at time t being exactly equal to the threshold of interest. And here are the solution. This is one solution for that when the threshold is 3 sigma sub 0. You will note that the response eventually reaches the threshold of interest. This is exactly the threshold. And so this is how that design point excitation is able to achieve the response of interest. One can show that design point excitation is the minimum energy excitation. We are essentially minimizing the energy in the excitation subject to the response at time t being equal to the. So in a sense, this is also the minimum energy by which the response reaches that particular threshold of interest. On the right-hand side, you see the hysteretic loop of the oscillator, and you can see that initially you have small excitation cycles, and so some dissipation there, but eventually you get a big cycle, and that is what puts you at the threshold of interest. It turns out that the tail equilinear system strongly depends on the threshold that you select. And this is the distinguishing character of tail equilinearization method versus conventional linearization method. In a conventional linearization method, there's one linear system, equilinear system that you find, and you have to apply that for all thresholds. But here, for each threshold, you end up having to get a different linear system. And for that reason, we designate the unit impulse response function and the frequency response function of the equilinear system as functions of the threshold x also. So we like to emphasize that these are functions of x. You will note for the same oscillator that I described, these are, I'm showing on the left the unit impulse response function of that oscillator for a very small threshold of 0.5 sigma sub 0. This looks like unit impulse response function of a linear oscillator you would see behaving like that. Now let's go to a higher threshold, 1.5 sigma sub 0. The blue curve now is not the typical impulse response function that you have seen. In fact, the first cycle is big. It doesn't return as much back. It doesn't go much beyond 0 in the negative range, and it quickly dissipates. Of course, the dissipation is because of the hysteretic damping. And you can see throughout that it dissipates very fast. On the right, you can see the hysteretic loop. And finally, at 5 sigma sub 0, very high threshold, you can see that effect even more. Dissipation is even faster. And so these curves are not typical of the unit impulse response function you would see for a linear oscillator, because these are special oscillators. And probably these are very high order linear systems. We don't know what their orders are, but very high order. In the frequency domain, these are the frequency response functions of these linear systems at the very low threshold, what you would expect from a frequency response function of a linear system, a very strong, sharp peak at the fundamental period or frequency of the oscillator. Here it's something like 1.3 or 4 hertz. And then we look at higher threshold. Now there's hysteretic behavior happening. The peak drops. Not only the peak drops, but also the frequency content goes towards lower frequencies. There is much richer content in the frequency, in lower frequencies than at the resonant frequency. And this phenomenon, maybe this is the higher harmonics of this linearized system. If you go to much higher, now the resonant peak has practically disappeared. There's a very high content of low frequency, and because we're dealing with a softening system, and so the system is behaving having much lower frequencies in its response. Because of the dependence of the telecom system on the threshold, this method, telecolonization method, is able to capture the non-Gaussian nature of the response. Here you will note that this beta of x for a linear system, you remember, was proportional to x. That was why it was Gaussian. But for a nonlinear system, this reliability index is a nonlinear function of the threshold. As a result, it's able to capture the non-Gaussian nature. Here is a picture of the linear case is when alpha is set equal to 1. The nonlinear case is alpha equal to 0.1, and you can see that beta is a nonlinear function of the threshold. Incidentally, the red and blue curves are two similar calculations based on time domain and frequency domain. This is this probability distribution. This is the tail probability, complementary CDF, exactly what you see up there. So not showing. We are showing several curves. The top curve is the case of linear oscillator, that is alpha equal to 1. The error curve is based on frequency domain term, time domain term. They give you practically identical results. And the I bars are Monte Carlo simulations. Of course, at the high thresholds, probabilities are very small, and so the uncertainty in the number of simulated, I believe 1 million or so simulations were used. So at the very high thresholds, there is significant uncertainty in the simulation, but the mean estimate is very close to the line, as you can see. This is the probability density function of the response at that point in time. And I said that this is going to be non-Gaussian. In fact, if the response is Gaussian, in this plot, the curve would be a parabola, would appear like a parabola because it's a logarithmic plot. And in fact, you can see for the linear response, the curve is a parabola, whereas for the nonlinear case, it's not a parabola. The tail sort of goes down almost like a straight line in the log space. And of course, Monte Carlo simulation also verifies that this is a good approximation. One of the interesting aspects, I'm not giving proofs, but the proofs are in the papers that are cited in the web. One of the interesting aspects is that the tail equilinear system is invariant of any scaling of the excitation. That is, if you take the excitation S times f of t, then you get the same linear system no matter what S is. This makes this method particularly useful for fragility analysis. So for example, this curve, this entire fragility curve, fragility is conditional probability of event of interest, failure event of interest, in this case, the tail event happening, conditioned on a scale of the excitation. In earthquake engineering, for example, they do it conditioned on the peak ground acceleration. All this curve has been developed by using one design point because of this particular property. For stationary response, it turns out that the tail equilinear system is independent of time t. So you just need to do analysis at one time to get all the statistics that you want. For example, you can get point-in-time distribution. We just did that 2 slides ago, so I will not show that again. But you can get mean upcrossing rate at any level. This is the mean upcrossing rate compared with Monte Carlo simulation. In the linear case, you can get first passage probability. You can get the probability that the maximum, say, of the absolute value of the response over a certain duration, capital T, exceeds a certain threshold. And that is given on the right-hand side. This is what typically you want. You don't want the point in time. You want distribution over a duration of excitation, of the maximum over a duration of excitation, and that is shown on the right side. But that point in time is a key for getting that. For broadband excitations, as you would expect from random vibration, linear random vibration, the tail equilinear system is not too sensitive to the frequency content of the excitation. As a result, one can use a white noise input or tail equilinear system obtained for white noise input for all kinds of broadband excitation. So you do it once and then you have several different broadband excitations. You can use the same tail equilinear system for all that calculation. Here on the left, I'm showing the first passage probability for 10 seconds for a wideband input. And there are several approximations shown. One is the exact TEL that is using the broadband excitation. One is TEL based on white noise, and you can see there's very little difference between the two. And the Monte Carlo simulation is also shown. On the right-hand side, the tail equilinearization method based on white noise is this, whereas the exact one is slightly different. So for narrow band, it doesn't work as well. For non-stationary processes with smooth evolution in time, one can obtain the Taylor equilinear system at a critical time and then use it throughout. Marco Brocardo has been developing this, and he calls it evolutionary TELM. Some of you might be familiar with evolutionary analysis. We have a modulating function in time and frequency, and then input-output relation is in terms of this modulating function m of frequency and time. And what is done in TELM is to replace this impulse response function by the impulse response function of the Taylor equilinear system. Here's an example of that kind of analysis. On the left is the modulating function, only function of time, so it's a uniformly modulated function. On the right is the power spectral density, so we have a non-stationary response. And here you can see the reliability index. Dots are exact TELM at separate times, and the red curve is computed at only one time and then extended by use of that integral. These are the evolutionary FRF of the response at different times using this through different methods, and you can see that it captures the evolutionary nature of the response quite well. TELM can be applied to multi-degree of freedom systems. In fact, there's no more complication because the complication is in discretizing the excitation. If you have 1 degree or you have multi-degree, the excitation might be the same. And so in terms of complexity, it doesn't get more complicated. Of course, computation of response of a multi-degree might take a little longer time. Here's a 6-degree of freedom hysteretic oscillator. In this case, the hysteretic model is a smoothed bilinear elastoplastic behavior, and you can see for first floor and the 6th floor. And these are the equivalent frequency, the FRFs of the equilinear system. You can see that it captures the modes. For example, at the first story, there is a significant change in the peak contribution of first mode. For the 6th story, the significant change is happening in the contribution of the 2nd mode. And these are comparisons of the results. The approximation doesn't work as well for the first story as it does for the 6th story. Finally, TELM can be extended to multi-component excitation. In fact, Marco Brocardo has a paper this afternoon using this method for a base, looking at a base-isolated versus not base-isolated structure with hysteretic behavior. Here is an earlier example that he developed of a structure with bi-component excitation, 2-directional excitation. The response of interest is this wall number 1 in the bottom. We are looking at the interstory displacement of that wall. And now you get these plots, trajectory plots of the design point excitation and design point response. Because x direction is the response quantity of interest, you can see that the excitation is more extending in the x direction than in the y direction. And these are the equivalent linear systems in terms of their frequency response functions. Finally, of course, no method is perfect, and every method has its own limitations. The main challenge in TELM is that it requires repeated computations of the nonlinear response. Repeated, when I say repeated, maybe around 10 or 20 times at most. But the nonlinear calculation these days is not a big issue. The bigger issue is the gradient. As I said, we use direct differentiation method. And if you're interested in using this, you need to really develop, and it's not, this topic is well developed in the literature. Many people have contributed, and there are codes that do this. I recommend this. I don't recommend using finite differences. You could use finite difference just to experiment, but then for implementation you need DDM. This also makes it clear that the nonlinearity has to be, the constitutive law has to be such that the response is continuously differentiable. Otherwise, you can't define a tangent plane. So, for example, purely elastoplastic oscillator you cannot use. You have to smoothen that elastoplastic. For that reason, in fact, in open seas, we have smoothed elastoplastic, smoothed J2 plasticity laws, where you control how you smooth the transition. So essentially, the transition between different states has to be smooth. One has to acknowledge that real systems have smooth transition. Elastoplastic is just an idealization we use. So I don't think this is so critical, but you need to use smooth laws. The linear system, the limit state surface must be somewhat well behaving. So from experience, we know certain things don't work. For example, Duffing oscillator does not work well if the stiffening happens very rapidly. If the system is stiffening very rapidly, and I can explain why the reason. Or when abruption, for example, contact problems or bifurcation problems may not be well suited. This method may not be well suited for those problems. And also this method, as of yet, we have been thinking, but we haven't come up with a solution for degrading systems. So this is something really meaning staying out. So I hope I've convinced you that TELM is an alternative equilinearization method for nonlinear stochastic dynamic analysis. It is non-parametric. It captures the non-Gaussian distribution. It offers superior accuracy for tail probabilities. It is particularly convenient for fragility analysis, can be applied to stationary or non-stationary response, can be applied to multi-degree of freedom systems, multi-component excitation, as I showed. It requires continuous differentiability of the nonlinear response, so that's a restriction. And just like other linearization methods, its accuracy depends on the type of nonlinearity that you have. Thank you very much.
Thank you very much, Professor Der Kiureghian. I would like now to invite Professor Krotis and Professor Bazan up on the stage with me so they can share with us our thoughts. Please join me in welcoming them.
First of all, I would like to congratulate Armen for an outstanding and illuminating lecture.
Thank you.
I must admit I haven't worked on random dynamics, but I have been interested for many years in tails, particularly in connection with fracture and damage, tail probabilities. And I think the comparisons are rather interesting and could invite a number of questions. So one is the question that in fracture and damage, probabilistic, the question of scaling is paramount. Does the question of scaling arise here? Of course, in dynamics, it's a more complicated problem, but still scaling is a fundamental question. If you go from a large system, a small system to a large, can one learn something about the large system from the small one? So that's one question. And the second one, you mentioned at the end the type of behavior. There is ductility or brittleness. Now that can make an enormous difference. As far as I understand, most of the analysis is based on assumption of ductile response of the structures. Yet in applications to earthquake, that's rare. Structures soften, they're not ductile, reinforced concrete structures, And that can change the response enormously, as it does in fracture and image mechanics. And I have 3 more questions, but maybe these will be the first ones.
On the issue of scaling, of course, we have looked at scaling of the excitation, as I mentioned. But we haven't thought really of scaling issues with the structure. In terms of fracture, obviously, if the constitutive model, if the method is being used for that, there will have to be some kind of a smoothing, and maybe that, just like I sympathize with you because I'm not in your area of fracture, so but I believe there has to be some kind of smoothing of fracture mechanics laws to allow this to happen. I think TELM can be a way of exploring whether the scaling from micromechanics to larger system is important or not. It might be a vehicle for doing that, but itself, I don't see it being affected by that. Regarding the second, the whole point in earthquake engineering, design of structures for earthquake resistant, is to provide the necessary ductility by providing the proper reinforcements in the joints and the proper development lengths and so on. So we're assuming that a structure can take that kind of ductility that we modeled. But again, this is something that one can investigate if what is the probability of ductility exceeding what you have accommodated for. So that would be a catastrophic failure. So this could be a way of investigating that. We could easily determine the probability that an interstory drift will exceed a level that is accommodated by the particular reinforcement that is provided.
I agree that ductility is the objective, but if you look at test results, it's not achieved. Structures in earthquake often fail by shear, which is always brittle, and even in the tests of the T specimens, hysteretic, we always stop when it starts softening and go back, and it's always the softening is there, which is not ductile, yes, which is localizing.
Well, yeah, the softening issue, as I mentioned, degrading systems we cannot handle, period, at this time. Whether we can do it in the future, I don't know. But if the system is softening and degrading with each cycle, then that's a very difficult problem in stochastic dynamics, because even if you have a stationary excitation, the response is not stationary for something like that. So that we cannot, as I mentioned in my summary also, we cannot handle.
Yeah, okay. I don't want to take all the time.
Maybe we can come back.
Yes, okay.
Thank you, John Paul, and thank you, Armen. I've always admired your work from when you were a little kid.
Thank you.
I'm just giving an age difference there. Also for an excellent talk that balanced a very complicated situation with presenting it in a way that we could understand the concepts of it very easily, perfect for a keynote. And of course we want to ask, give an opportunity for questions from the audience too. So I just have one question. At the end you talked about the extension to multiple degree of freedom systems and showed one of the 6 different degrees of freedom and said the number of random variables doesn't change. I was really interested because I think there's a lot of application of something like this for a multiple degree of freedom system where you have a lot of limit states with fairly similar beta values. do you think that the method could be extended in a way that could apply to a multiple degree of freedom system with a fair number of similar risk limit states?
Yes. For example, in a multi-degree of freedom system, suppose we define failure as any of the stories exceeding their corresponding safe inter-story drift levels. Then that becomes a systems problem in the context. Yes, we can solve that. Because what we do, essentially we linearize, we are linearizing a system, so we have to deal with not the normal, cumulative normal distribution, but multi-normal distribution. And we also need the correlations between them, which has to do with the inner product of the A vectors. So, but of course, it would mean if you have 6 stories and 6 limit state functions, it means 6 times computations. It's as many times computations. But all the information is there for that kind of systems analysis.
Okay, interesting. Did you want to turn to the audience now?
Yeah, thank you. Well, thank you very much, both Professor Korotis and Professor Bazan, for your comments and questions. I think we have 5 more minutes, so if there is any question or thought from the audience, we can entertain that before we close the first plenary session. Professor Paulino.
Yes.
Very interesting lecture. Just a curiosity. I found really nice the fact that in one of your slides you showed that for a linear system and Gaussian processes we can get a closed form solution for the reliability index.
Yes.
And I was very excited about that. Can you get that closed form solution for other situations?
For what equations?
Other situations. Maybe if the system is nonlinear or non-Gaussian. And
maybe for very special nonlinear systems, maybe. I doubt it, but for linear system, yes, you can. I doubt it if for any nonlinear system, maybe very simple quadratic. For example, well, let me backtrack. For Duffing oscillator, which is an elastic nonlinear system, oscillator, just oscillator, single degree of freedom, you can get the design point. It turns out the design point is the mirror image of the unit impulse response function. So you don't need to do iteration to find the design point. All you have to do is compute you take the Duffing oscillator, displace it by the threshold of interest, let it vibrate, free vibration, numerically compute that free vibration, then take the mirror image. That becomes the design point excitation. For elastic oscillator, not multi-degree freedom system, for elastic oscillators, you can always do this. Not Duffing alone, but any kind of elastic oscillator. And that has to do with the fact that the design point excitation is the minimum energy excitation that puts the response at the level of interest. And it turns out that if you displace an elastic oscillator by that threshold, it will find the minimum energy way of dissipating energy to go back to its original state. So that's why when you take the mirror image, you get that. So that's not a closed form solution, but at least you don't need iterations. You go multi-degree, we haven't been able to find, there are some ideas, but not exactly.
Thank you. Is there any more quick question before we close? I think I see one hand up there.
Yeah, in your presentation, you assume that you have only one design point, but for 100 or 1,000 random variables, you might have more than one design point contributing to the failure probability. Can you comment on this?
Yes. Yes, multiple design points are an issue in structural reliability methods. And there are ways of handling that. In this case, we've never encountered that, particularly with hysteretic systems. We've analyzed many, many systems. We've never encountered that. You really have to work very hard to get a problem where this happens. And years ago we did, and we have a paper where we worked very hard to formulate a problem to have multiple design points. But say if you are going over I showed a sequence of design points. If you're going over a sequence of design, it is possible that the trajectory goes, at some point, there's a second design point, and then trajectory continues there. So you have sort of trajectories that are not continuous. That could happen, although we haven't encountered that. If that happens in that range of that threshold where this break happens, probably the approximations are not good enough. And then so I would, as an engineer, what I would do is forget about that section there and just do matching between the other portions, avoid that break. But as I said, we've tried and we're cognizant of that fact, and we haven't come across any situation where multiple design points happen for these kinds of systems, for hysteretic systems, and it's where most of our experience has been.
Well, I think we have reached now the allocated time to this lecture, so I'd like to close it and thank one more time Professor Der Kiureghian.
Thank you.